Good evening, everybody. This evening we welcome Dr. Martin Fullekrug from Bath, and he is a University of Bath research professor, and his primary research focus is on the Earth's electromagnetic environment, which includes the atmosphere, near-Earth space, and solar terrestrial physics, with an emphasis on applications such as lightning discharges, space weather, and communications. Dr. Fullekrug has written 2 books, served as a guest editor on several special journal issues, and has several papers in worldwide scientific literature. He is a founding member of the C.T.R. Wilson Institute for Atmospheric Electricity, and is on the electoral boards of Surveys in Geophysics and Frontiers in Earth Science. So please, everybody, put their hands up and together and welcome Dr. Martin Fullekrug. Thank you. Over to you, Martin.
Thank you very much for this lovely introduction. And thank you very much for inviting me, which gives me the unique opportunity to share with you my field of work, which has to do with lightning discharges. And in particular, because you are interested in space, I thought for this presentation, I will talk about lightning into space. Lightning into space, you see here on this first slide, where you see the mountain range here in front, and then behind there is this beautiful display of colorful blobs coming up. This is known as a sprite. What you cannot see is that behind that mountain range there was a thunderstorm and lightning. These sprites, as they are called, they are somewhat similar to northern lights. So except that northern lights, they happen above the area of the sprites. So we have like a very continuous display of illuminations from the lightning in the troposphere, then the sprites in the middle atmosphere, and the northern lights in near Earth space. So the plan of this presentation is to first introduce you to the basics of lightning, and then move on to lightning into space, these sprites. And the last bit of the presentation will be how we study them. For that, we use radio waves, the same radio waves that used to work for radio and television. And this is our main research focus. So to produce a lightning, first of all, we need thunderclouds. And thunderclouds, they tend to develop when 3 different conditions are met in the atmosphere. The first one is we need warm air. So most of the thunderstorms in the UK, they happen when it's relatively warm during the summer months. The second thing we need is moist air. So in the desert, for example, it is very hot, but you will rarely find any lightning because there is no moisture. And the third ingredient to produce thunderstorms is that the upper level of the atmosphere allows actually bubbles of these clouds to develop vertically up. During this upward motion, which is known as convection, you have the air starting to produce droplets. And then when you go higher in the atmosphere, around 5 kilometers, they start freezing. This height of about 5 kilometers is incredibly important because this is where ice and water coexists. And this is the area where the rhyming graupel and ice crystals, which collide with each other, they start producing a charge exchange. And the graupel, because it's heavier, stays in the cloud, whereas the ice crystals, they are carried aloft. And that, because they are then differently charged, it produces a difference in the charging mechanism. And then that results into discharges once a certain electric field is exceeded. And that is what we know as a lightning flash. Now, the vast majority of lightning flashes, they stay entirely inside the cloud, and we can see them essentially as a flicker. Now, if the thunderstorm is more than 20 kilometers away, we don't hear the thunder anymore because it propagates for about 20 kilometers. But the flicker we can see over hundreds of kilometers. If you are positioned on a mountaintop and you have storms and you know where to look, you can see this over 300 kilometers, very often as reddish and orange type of lights. Now, all this intra-cloud lightning is normally not of particular interest to us as human beings because it doesn't come to the ground. 90% of all the flashes, they are entirely constrained to the cloud. And it only gets interesting for us when the lightning actually comes to the ground. And this is about 10% of all these flashes. Now, when we have a lightning flash to the ground, it develops out of the flashes which are inside the cloud, and it propagates relatively fast down to the ground. And once it starts connecting, then in the majority of lightning flashes, it moves electric charge. It moves electric charge upwards to neutralize the electric field. However, only 90% of these lightning flashes that are coming to the ground are these so-called negative lightning flashes. 10% of these lightning flashes do the opposite. So in this case, then, they're called positive lightning flashes. And these positive lightning flashes, they have become very important for a variety of reasons. Sometimes they're called mega flashes, sometimes they're called spider flashes, and they have a massive impact. And this impact is very diverse. So you see here the lightning flash which is coming to the ground, but then to sustain these very, very strong flashes, the lightning inside the cloud propagates over very long distances and draws the charge from other parts of the thundercloud into the original channel, and then it starts having a continuing current flow. Now, this continuing current flow is very, very important for lightning protection because the continuing current flow can actually burn metal. But also the intra-cloud flashes are very important because they can produce a stress on the atmosphere and effectively make it glow. And these are these lightnings into space that I was talking about. Now, this is an example that you see here from such kind of mega flash. But you might have heard in the news that there's now a geostationary satellite that observes all the time over the United States. And they discovered there that these flashes, they can go over hundreds of kilometers, 300, 400, 500 kilometers. So there will be new records that will be broken thanks to these new observation capabilities. So let's have a little bit of a closer look at the lightning types. So in slow motion movies, what you can see in the beginning of a lightning flash, you have what is called the leaders. Leaders are these things that are propagating slowly from the cloud to the ground. And they are trying to find the path of least resistance. And the vast majority of these leaders, they are unsuccessful to find the ground. But once they hit the ground, then they can establish a connection between the cloud and the Earth. And then you have a lightning channel that develops in which the current flows. The reason why this happens is because the lightning flash attaches to the Earth where there's a reservoir of electrons, and that reservoir is then drained. And at some point, the plasma channel becomes too hot, and then it starts disintegrating. However, very often what we see is that the lightning flickers. And this is because each lightning flash, on average, has 3 different strokes that are happening in time intervals of about 15 milliseconds. So they are very fast consecutively. And I was showing before the continuing current associated with this mega flash. In this example, you can also see this continuing current at the very end. So this is this very end where there's a continuing discharge And then you see even some blobs inside of these lightning channels. So, quick summary of all of the lightning types. So we have the thundercloud here, and then we have these leaders, which are normally having a step length of 100 meters inside the cloud. But the closer they come to the ground, the shorter these steps get. And this is very important for lightning protection. So a standard rule is that these steps are about 20 meters long once they are close to the ground. That means to be protected from a lightning strike, you want to have something that's higher than yourself in about 20 meters distance. Then we have the return stroke, which is the continuing, a more continuous current flow. And then we have the dart leaders or consecutive return strokes that are happening inside the same channel. And at the very end, we get a continuous illumination. This is known as the continuing current. And all of these processes, they happen on very different time scales. So the step leader tends to happen on a time scale of 1/1,000,000th of a second. So it's incredibly fast. The return stroke is on the order of 50 to 100 microsecond. And the continuing current, this is on the order of larger than 40 milliseconds. Just for comparison with the human reaction time, the human reaction time is on the order of 200 to 250 milliseconds. So it's 5 times slower than even a continuing current would be. Now, one of the most asked questions is, well, can we harvest the energy in a lightning flash? And that is a very interesting question. If you look into your textbooks from school, you can make estimates and calculations which bring you to incredible numbers like megajoules in a lightning flash, or gigawatts, which is actually similar to a nuclear power plant. However, these large numbers, they don't take into account that lightning is actually relatively fast. And because it's very fast, it is actually very difficult to charge up your car battery. So in your car battery, if you wanted to charge your car battery, it takes about 5,000 flashes to charge it up. I guess what I'm trying to say is that these numbers, they're more of a physical interest rather than of a practical interest. So the situation is there somewhat similar like with nuclear fusion at the moment. Nuclear fusion is getting longer and longer. I think 30 years ago when they started, they were on the order of microseconds. The latest record I heard about was about 5 seconds, but they're still very far away from producing continuous energy, which effectively is the key requirement to be useful. So this is the basics of lightning. Then let's have a little bit of a look at what we know about lightning. And one of the key topics there is to know more about global lightning. Thanks to the space age, we have now satellites which are whizzing around the globe and measure lightning all the time. And so you see here one of the first pictures that was taken over about 10 years of recordings from various satellites. And that gives you then a global lightning map. So they measure the optical pulses that you can see from the cloud. And red and black means like a lot of lightning flashes, and blue and greenish means like a few lightning flashes. So you see that the big winner here is the Congo Basin, where we have lightning flashes practically all the time. There's also a very strong area here in the Himalayas, in the southern Himalaya, where the thunderstorms get stuck and because of the mountain range, and then they discharge very well. There's another lightning hotspot, which is well known in Venezuela, that is called Lake Maracaibo, which used to be called by seafarers a natural lighthouse, because the lightning was practically over there, always there. We have very little lightning in the polar regions, although because the polar regions, they warm up relatively fast when compared to the rest of the planet associated with climate change. These thunderstorms at the moment, they keep on migrating northward. So this is considered to be somewhat the minus canary of global climate change. We also have practically no lightning in the Antarctic. And there's a few places on the Earth where there's also very little lightning. This is in the Pacific Ocean, if you are below the intertropical convergence zone. And also here's one of the spots where there's almost no lightning in the Eastern Sahara. So this is associated with the weather pattern. But one of the key properties of lightning that you immediately see is that's mainly a continental phenomenon. So you immediately see that over the sea, there's much less lightning. And this is, of course, because there's less thunderstorms. So you can see that there's the trade winds. So here we have easterly winds, which drag out the thunderstorms into the Atlantic. And here in the mid-latitudes, we have the opposite. We have the westerly winds, which drag out the thunderstorms into the different direction. So these are all meteorological phenomena that are pretty well understood. If you go to Britain, then you see here that there's a relatively small amount of lightning flashes. If you look up the numbers, then you will find there's about 3 flashes per square kilometer per year. And, you know, the University of Bath is probably one of the highest campuses in the country. We are about 200 meters, and my office is on the 4th floor, on the top floor of our department. We have beautiful views towards the west, and I can happily confirm that this number of 3 is actually quite good. So on average, over the 20 years that I'm working there, we have about 3 thunderstorms a year which are crossing the campus. So it's actually a very nice way of confirming roughly the numbers. You can also see that most of the lightning here in Britain is actually in the southeast. Now, these type of maps, they're incredibly important for government and policymakers. So why is that? Well, it's not so much because of the lightning, but more closely related to severe weather, which will increase during climate change. Severe weather by the meteorology community is defined as flash floods, wind and hail. So where flash floods is unpleasant because of the flooding, wind is unpleasant because trees lose their branches and they might drop on people or on their cars. And then we have damage from hail on vehicles or crops. And if you are unlucky, you get hailstones, which are actually very, very large. And if you get caught up in those, it's actually quite painful, I can tell you. The lightning is also important because it damages equipment, mainly for power distribution networks, like Western Power, for example. They have to make sure that there is no fault on the power lines, but if you have a current surge, then it can fail the equipment. So you need to have proper equipment in place to make that not happen. But it's not only power distribution. Think about HSC, for example, the high-speed trains. The signaling equipment is also very sensitive and needs proper lightning protection. And all these type of things need to be considered, especially on over longer time scales. So at the moment, the Met Office is very busy trying to make predictions over the next 30, 40 years. What will be the lightning under climate change, and what will be the associated threat levels associated with building new infrastructure, which requires power. But lightning does also other things. For example, it ignites wildland fires. Famous example is in the United States, where there's regularly fires ignited, especially during drought conditions. And last but not least, lightning also causes casualties. Here in Britain, we have about 2 or 3 people a year, mostly hikers, which are unprepared and hiking in the mountains during thundery conditions. In the United States, we have about 100 to 200 people a year who die, mainly people who are working outside in the fields. Actually, I should say that casualty is you have about a 50% likelihood to die if you are struck by lightning. So you have a good survival chance, and the likelihood to be struck by lightning is about 1 in a million. So it's very similar to winning in lotto. The largest number of casualties we have in Bangladesh. So that's in this area here. And the reason for this is that there's a lot of thunderstorms but the people, they have no choice. They have to go out onto the farms and do the harvest and get their food. So even though there's thundery conditions, they have to walk out. And that is a problem. In a house, in a car, in an airplane, everything that has a shell around you, you're normally relatively safe. But the majority of people who die from lightning flashes are normally people who are outside. Although it can also happen that under unfortunate circumstances, there's other casualties happening. Now, in total, we have about 2,000, 3,000 people dying every year. And I always like to call this the silent death, because if you have an earthquake or a volcano eruption, then you have many people dying at the same time. But over a year or over several years, it doesn't amount to the same numbers. One of the problems with casualties from lightning is that in many countries, they're even not recorded. So it's very difficult to know how many people are actually exactly dying from lightning. But the numbers are much larger than one normally thinks. So this is the global lightning situation. Now, how does global lightning change? And it's very intuitive to think that global lightning follows the temperature. And that is true to some degree. So we have the sun, and the solar insolation during a day drives the lightning activity. That means most of the lightning storms are in the afternoon, like 2 or 3 o'clock local time. And the thunderstorm activity migrates north and southward during a year. And that can actually be shown if you look at the lightning activity over the globe here on a flat map over the entire year. You can see the migration of the thunderstorm centers, which go up and down. So the vast majority of lightning flashes, they happen between the Tropic of Cancer and the Tropic of Capricorn. And that area, plus minus roughly 23 degrees, is actually, from an area point of view, covers about 50% of the globe. And this is where most of the lightning is. Okay, and with this, I would like now continue with lightning into space. So we have covered most of the basics of lightning. And now we want to have a look at lightning. How does it actually look like when we look from space? And in the Space Shuttle, they used to have payload cameras. Now we don't have any Space Shuttle anymore. Now we have the ISS, but it's very similar in terms of orbital height. Is about 300, 400 kilometers above the Earth. And then you can make movies from these video images. So this shows such kind of movie. The thing is upside down because the Space Shuttle doesn't fly necessarily straight like an aircraft. So it's upside down. And then this is how the lightning looks. So this is a massive storm. And each of these illuminations, these patches, is a lightning flash. And during these flights from the Space Shuttle, when the scientists, they looked at these movies, they found that there was a very curious phenomenon that you could just see at the very end. Let's see whether I can find that again. Yeah. So if you see here, you see the illumination from the cloud and a lot of scatter from the light that is associated with the droplets inside the cloud. So the scatters in all directions. There's also quite some dust in the atmosphere, which produces quite some scatter. And this is happening all the time. But what does not happen all the time, that is this little blob above here, which is an unusual luminosity. And this luminosity is clearly above, and you can estimate from these images that is going roughly up to about 80 kilometers height. And once NASA reported this, people got more curious about this. Of course, they wanted to study what this is. And what they did is they chartered aircraft which were circling around thunderstorms. So this shows a thunderstorm cloud top, and you see all these illuminations. And the aircraft flies around. And then every now and then you see these illuminations, which are known as sprites. They appear to be reddish. Oops. I'll try again. Yeah, they tend to be appear reddish. So this is a true color image, which was done with a color camera rather than black and white. Our eyes perceive this slightly differently because our eyes very often blue is perceived as white. And these sprites are actually happening so fast, you can see them with your eyes, but they're very brief illuminations so that you don't have the time to discover with your sensors in your eye, you cannot discover what kind of color they are because they're very brief. But from these images, we know that they are red, and they are red because they are mainly exciting nitrogen vibration lines. So that's one of the key things which produce the color. The color changes a little bit as a result of the pressure drop in the atmosphere as you go up, but that's roughly what it is. Now with sprites, it's very similar to lightning. You can have small and scumpy ones, and you can have massive ones. So this is an individual sprite, sometimes called a carrot sprite, but there's also something that's known as dancing sprites. And one of the most powerful ones that I've ever seen is this example. So you have here the cloud top. That's kind of like the this line here, which dips a little bit because the video camera was not straightened out. In the background, you see the beautiful star images. And sometimes you see a meteor here, or you see an aircraft passing by. Then you have the illuminations from the thundercloud top. And then you have here the sprites popping up. And you have this impression they kind of like go into one direction. And that's actually hundreds of kilometers. So from here to here is about 200 kilometers. And when you do exact analysis of this example, you see there will be 6 or 7 sprites in a row. One of the questions that people very often ask is also sprites producing thunder? And the answer is yes, they do. And we can actually listen to it. Okay, well, I should say that this is not the sound of these sprites for 2 reasons. Number one, these sound samples, they come from a different sprite. It was not the same sprite. But the other reason why it's not a true sound is because the thunder from sprites, because they are so large, they scale in frequency. And that means we have our normal thunder that fits into our ears. This thunder from sprites doesn't. It's too low for us to hear. The ear roughly stops around 20 hertz. So in the high fidelity range, we can hear from 20 hertz to 20 kilohertz. And below 20 hertz, we can't hear anymore. So you need special equipment, which is known as infrasound equipment, with which you can record them. And to make them audible, you need to speed up the recordings that they fall into the frequency range of your ears. So there's a little bit of trickery behind it. I think this is what I'm trying to say. Now, once people started to circle around thunderstorms, they very quickly found that besides the sprites, there's also other phenomena, which are a little bit harder to detect. So follow the advice, watch here, where there was a blue fountain of light, but it's very, very faint. Watch again. Did you see it? No. Okay, so here is in grayscale. It's easier to see in grayscale rather than in color. You see these fountains of light coming out of the thundercloud. So these are now known as blue jets. And you won't be surprised to hear that many, many more have been discovered over the time. So one which is called an ELV, these are concentric rings that are developing from in about 100 kilometers height, and they're expanding outwards very, very fast. They have a time scale of about 1 millisecond. Another thing that was discovered very quickly is that there's something that's called a gigantic jet. A gigantic jet starts from the top of the thundercloud, goes all the way up to 80 kilometers, and there's no interruption. And they're relatively slow. So they are living on timescales of about 100 milliseconds. So it turned out to be that there is a whole zoo of different types of luminous effects. And one of the latest discoveries in this area was what you can probably call dark lightning. This is when there is a particular type of leader discharge in the top of the thundercloud, which produces an electric field, which is very, very large, and then accelerates electrons. Then it produces an electron avalanche, which produces gamma rays and X-rays. So these X-rays, they ionize air molecules, and the electric field of the lightning accelerates these electrons. And because the air gets thinner and thinner as they go higher up, they produce something like an electron beam. And that can be detected in space. So besides the gamma rays and the X-rays, you can also measure electron arrivals in space from this type of event. So far we have covered lightning flashes, and we covered lightning into space. Now the question is, of course, we can make pretty pictures, but can we also make some quantitative measurements in terms of their actual impact? And the fundamental idea is that lightning, and also lightning into space, acts a little bit like a natural transmitter. So you have here a lightning discharge, and on top of that you have the lightning into space. And you can look at this as if there would be an antenna. So you have here an antenna which is transmitting radio waves for a particular application. And then what you would need to measure these signals is what is commonly known as radio receivers. So this shows a receiver that we have developed at the University of Bath, which is actually relatively simple. So you have a conductive aluminum plate, which is elevated above the ground, and you measure the potential against the potential of the ground. And that gives you an electric field measurement. And this electric field is directly proportional to the electric field transmitted by the lightning or by the sprites. Of course, you need a little bit more electronics. So in this box, you normally find batteries, you find a data acquisition card, you find a GPS clock, and you find a computer which does the recordings. And one of the things that's also very important is the amplifier. So because these signals, they are very, very weak, you have to amplify the signals first before you can actually measure them with a data acquisition card. And nowadays, because the radio receivers, they're relatively well developed, it is particularly advantageous to use receiver networks. So here you see, for example, 10 radio receivers, which are on a test bed, where we are just testing whether they log the electric fields consistently when you compare different receivers with each other. So it was a preparatory test that is somewhat similar to what people do in radio astronomy. In radio astronomy, you have these vast arrays of antennas. Very often they have 100 or 700 antennas, and then they use the antennas to image what the sky does. So they look at the sky and try to find out where does all the radio waves coming from. And that is something that we can also do with radio waves on the ground. And I wanted to share with you a little bit how this data roughly looks like. So we are measuring an electric field, but normally we are not looking at the electric field directly. Instead, we are looking at what is known as the radio rainbow. The radio rainbow is associated with a wavelength and similar to light. So the lower we go in frequencies, the longer the wavelength becomes. So frequency is small and wavelengths becomes very long. And this radio spectrum from lightning extends from about 1 hertz to up to 1 gigahertz. So in the gigahertz range, we call this microwaves. In the 1 hertz range, we call this quasi-static waves. And for lightning, what is particularly important is the frequency range around 10 kilohertz, which means about 10,000 oscillations in each second. And I wanted to give you a little bit of a feel for how the spectrum looks in terms of shape. So this is here the spectrum. It shows the electric field over this given frequency. And radio waves, they work in this way, that each range of frequency is associated with a particular service delivery. And it's quite busy because there's a lot of services to deliver. So let's have a look at 198 kilohertz. That is radio 4. So we can, one of the good things about this is that we can listen to it. So let's play that. Oh.
La gueule est morte, une nation.
So this was a transmitter that is located in France, in the center of France, and it delivers news items, but is also used as a standard reference for time. And here in the UK, we have something very similar. Which is at 198 kilohertz. That is radio transmitter, which is used for frequency stabilization and for timing, but is also used to set the gas meters in our house. So it's a very important transmitter for the country. Sadly enough, for some reason, I don't seem to be able to play this because I can't get to the start button. Anyways, so these are these transmitters which are delivering speech, but there's also other transmitters, for example, here at 100 kilohertz. So in 100 kilohertz, we have this problem that we want to simulate a GPS signal that is not so easy to be jammed. So imagine you have your GPS, which we have nowadays all in our mobile phones. The GPS satellites, they're about 30,000 kilometers away from us. And the transmitted power from them is very similar to a mobile phone. And that means when the signals arrive here, they're very, very weak. And that is very easy to disturb if there's electrical equipment around, either unintentional interference or even intentional interference. So if you have a service that you want to deliver, which is very secure, you want to have a backup system, and that is known as the long-range navigation system, and that sounds a little bit like this. So what you can hear there is a little bit like a Morse code, and you can even push this a little bit further and decode it. It's a very fast code, and if you know what the coding is, then you can infer what kind of messages are being sent. They're mainly intended for timing and navigation. There's another incredibly important service that is transmitted here for almost 60 years now, and that is what I like to call the heartbeat of the country. That's located at 60 kilohertz, and is a very straightforward signal. It sounds like this. So it is about the heartbeat. It's about 1 second. And this is of utmost importance. This is known as the radio clock. Probably you have a radio clock at home. Certainly in Bath and the university, all our lecture halls, they have radio clocks. The big advantage of radio clocks is they always set themselves. So they listen to this transmitter and then they set themselves according to whatever is being transmitted, which is particularly handy when the time changes in spring and autumn, and when there's a leap second and so on. So our clocks at the university, they're always synchronized on time. If you go lower frequencies, then we come to this peak here, and this is the peak that is coming from our lightning flash return strokes. And so we can also listen to lightning flash return strokes, which sound a little bit like this. So this is a little bit like a crackle. And the reason why it sounds random is, of course, because lightning flashes are essentially random. Now, these lightning flashes, they are not directly near us. At 10 kilohertz, the wavelength is so long that we can actually listen to lightning over thousands of kilometers. So this is lightning from Southern Europe and even Africa. Then you see these multitudes of lines here. This is associated with probably one of the largest man-made systems, which is the power grid. And this power grid produces somewhat a buzzing noise. Yeah. So this is our 50 hertz power lines and the harmonics associated with it. Now, this is, of course, a big disturbance for us as researchers because we are interested in the lightning signals, which I was saying before, they go down to about 1 hertz. And here's an example of lightning flashes that are heard at 20 hertz. That is very similar to the infrasound that we discussed from lightning into space, except that this is an electromagnetic analogon. So I can play this. So this is a very faint vibrational sound. So I play this again. See. You hear a little bit of crackle, and then suddenly you hear this, and this sound is a resonance. And that comes from the fact that at extremely long wavelength, the electromagnetic energy bounces back and forth between the ionosphere and the conducting Earth. And in the middle, there's the air, which is less conducting. And then in this circumstance, the electromagnetic energy can propagate around the entire world and comes back after about 120 milliseconds to interfere with itself. And that is known as Earth ionosphere cavity resonance. And with this, it is possible to listen to lightning flashes and lightning into space around the entire world. So 120 milliseconds, that's roughly half the reaction time. So how do we how can we imagine such kind of time scale? Well, if somebody steps on my toe, then it takes about 120 milliseconds to get to my brain and to be processed. And then it takes me another 120 milliseconds to push that person away. So this is roughly how these time scales are. So once we have looked a little bit into the radio waves, then the idea is now that we can probably do sprite detection because there is some current which is now above the Earth, unlike lightning, which is coming down to the Earth. And then we have the radio wave that we can probably pick up with our receiver. And it works particularly well if we have a receiver network. That is somehow similar to radio astronomy. And we were trying to make such kind of experiment, but sadly there was no lightning around at the time. But you have here an array of about 10 receivers that are used for such kind of experiment. And the way radio astronomy works is we have these electromagnetic radio waves, which have here a pulse that, of course, is received at each receiver with a certain time delay because of the elevation angle. And then it appears on our records as a delay. But by calculating the delay, we can superimpose each of these waveforms. And this delay is then directly proportional to the elevation angle. And then we also reduce a lot of the noise by using that waveform. And from that, we can then make images of the sky. So this shows how the sky looks like above Bath. So reddish colors and dark and white colors, they are large energies. You see here these spots, which are all associated with the energy from radio transmitters. And there's one here which is very sharp, that is a transmitter which is in northern France. And then here on the top, there's relatively little, because these radio waves, they don't propagate through the ionosphere. So we get some shielding there. And then once you image the sky above above a certain area, you can also make super resolution experiments. So you can see, for example, here we observed a blob, which then, if you do a high resolution analysis, turns out to be actually two sources, which are just very close together. Well, you can also image lightning in the sky. You see here, there was a lightning storms were going on in southern France, and we had our array operating here in Bath. And you can see from each of these directions that there was a lightning center at various angles. And some of this lightning energy even arrives at a certain angle from the sky. Well, in this, you can make a lot of different images of continuum radiation. Continuum radiation at these low frequencies is largely under-investigated. That is something that we are particularly interested in. Continuum radiation is something where you don't have a clear signal. It just looks to you like noise, very similar to radio astronomy. But if you map it on the sky, you start seeing blobs. So you see here, there's all different blobs. And then we are trying to find out what are actually the sources of these radio waves. Well, and with this, I would like to end up my talk. I think we have seen a little bit, we learned a lot about lightning and thunderstorms, which then produces numerous various effects of illuminations above the thundercloud, including electron beams. And we looked a little bit at the strategies adopted from radio astronomy, how we can measure the electrical signals from these creatures. And you won't be surprised to hear that this is a very a topic of large interest, mainly because very soon we will have a European satellite which observes lightning in Europe and in Africa, which is mainly there for looking at changes to lightning activity associated with climate change. One of the most asked questions at the moment from public media is, does lightning increase with climate change? Do we have to prepare for it? What do we do? Do we need to be better protected and so on? So there's the MeteoSat third generation will have a camera and then record lightning from about 40,000 kilometer distance in the future. And with this, I would like to finish. I hope you enjoyed my talk, and I look very much forward to your questions.
Martin, thank you very much. Could I ask you to stop sharing your screen, please? So, could we just have the front lights up a little bit? Martin, thank you very much for a really interesting talk. As always, digital hands, please. For people who are joining us virtually, and we'll try and feed in questions from the room as well. So, Mick Nichols.
I'm just interested in the camera that's actually recording these things. Is it just an ordinary camera, or has it got special filters, or?
Yeah, it's really surprising. So the reason why lightning into space is so heavily investigated now is mainly thanks to the video camera development. They were first recorded about 25, 30 years ago when video cameras became mainstream. And nowadays, if you have the the latest Sony chips that are more or less in almost every camera nowadays, the camera itself is just an electronics package for various applications, but the chip is normally always the same or very similar. They all come from Sony, and they are perfectly capable to see these without any problems. So we have bought consumer type cameras for 150, 200 pounds, put them on a tripod, go to a mountaintop, which very often is very cold, even though it's summer, and you start seeing these sprites popping up. Yes, it's surprisingly simple. It's actually quite interesting because we had quite some touch with the astronomy community people who are doing meteor observations. You know, the funny thing is that we very often see meteors, and they actually very often see sprites. So before, it was not known to us whether there are sprites in the UK. And for us as scientists, it's not very time efficient to make observations if there's only a sprite here and one there. But these meteor observers, they observe them over all the storms in the UK. It's just amazing. They're everywhere, even on small storms. You just have to sit and wait.
Thank you.
Okay. Gary from Mid-Kent.
Hi, yeah, thank you. Thank you, Martin, for a really interesting talk. In fact, sprites fascinate me, and I know they're relatively recent discovery, but I wondered, have they always been here on Earth, since we've had weather, full stop? Or is it something is it something to do with our climate over the last, few eons that have created the situation, the circumstances for them, or do we not know?
I think that's a fantastic question. I would love to know the answer to that question. So there's several theories there. We know that lightning also has a component which is associated with dust. So it might very well be that the sprites just pop up because it's getting more dirty there because of all sorts of debris, probably meteor ablation, whatever. This is largely unknown. It's just pure speculation. The other thing that you're saying, have they been always there since there's weather? I mean, weather has been around on this planet for quite a while, but it's cozy warm. It's only since the last 10,000 years where humanity developed. Before, the Earth was pretty much an ice ball and it was very unpleasant here. So the tricky question is that at the moment, the lightning community has no idea whatsoever what the lightning during an ice age was like. How much lightning was there? How abundant was that? And so as a result, we also have no idea about the sprites. And there's no cross-links with the communities who could probably help. So at the moment, this type of question is largely unknown. But it is a super interesting question, certainly.
Oh, thanks very much.
Okay, Gary. Martin, a question from me, please. The sprites, are they discharging into another layer of the atmosphere, or are they actually discharging into space?
Yeah, that's also a very good question. The theory is normally that the electrical energy is consumed by what is called impact ionization. That means you have an electric field, and then you have lightning electrons which are stripped off from the energy from the lightning flash, and upon recapture of these electrons, they start producing light emissions. Now, what they do when they develop, they have these sprite streamers, which normally develop from the top, so they're effectively moving charge, but not over very large distances. So it's a little bit like the same model that you have like in a conductor, where the drift velocity of electrons is actually very small. And it's more like you push one electron in here and one electron falls out at the other end, and that then appears to be a current. And that's the same with these sprites. Whether they produce something further up in the atmosphere, there have been very interesting observations that very strong sprites, they can produce a heating of the ionosphere, and that can be a secondary source of what is known as ionospheric Alfvén resonances. These are standing waves which are developing along the magnetic field lines somewhere between 200 and 1,500 kilometers.
So a follow-up question then would be, is there any correlation between sprite numbers and the magnitude of the solar wind, or the intensity of the solar wind?
Not that it would be known. So the current idea is that solar wind, changes over time scales of decade, associated with the solar variability. So the more when we have a lot of sunspots, then the sun is more active, and then the solar wind is kind of like enhanced. And what that does to the ionosphere is that there is more charge. That essentially means the ionosphere comes down a little bit. And the overall effect of that would be that the conductivity always screens the electric field and reduces it. So as a result, what one would expect is that it's less likely for sprites to occur. So the current thinking is, which is entirely a speculation based on theory, is that during solar maximum, there should be less sprites. But it's very difficult to prove because they're not always there. So there's a very large statistical variability. So you would need to have observations for a long time and continuous. And one of the prime spots where that could be observed is, for example, in the Congo Basin, yeah, because you have lightning almost every day. The problem with Sprite observations in the Congo is there's too many clouds. There's a jungle, and that produces constant evaporation, and that makes you always haze. And you can't see the sprites through haze. So this is like the end of the story, sadly.
Okay. Tony Hudd.
Yeah.
Tony, can you unmute yourself?
Yeah. Hello. Yeah, I'm wondering about, is it feasible to make one giant conductor, lightning conductor, on a big mast that will attract lightning to itself rather than to churches and trees and wet cows and lots of other things? Would that be feasible?
Yeah, of course. I mean, this is a little bit like lightning protection works.
Sorry?
This is a little bit like how lightning protection works. So you make your house, well, only a few centimeter, like 20 or 40 centimeter larger with a lightning rod. And then the likelihood of the lightning to strike there rather than somewhere else is actually increasing. And so as a result, then it strikes there and then it goes around your house. So if you have a flat plane, like for example, a meadows, which is all very flat, and you have a very high tower there, then of course the lightning would hit there. We know this actually quite well from skyscrapers. You know, Toronto has a wonderful skyscraper which is hit by lightning all the time. And on the top floor in the exhibition, they showed you all the beautiful pictures. So it's actually very nice. Yes.
But I mean, if it's purpose to build a big tower with a light and make it into a lightning conductor, and there wouldn't be all these little ones around. It should all go to the big one.
Well, not all. That's a very good point. Lightning protection is not perfect. So I was saying one of the rules of thumb for lightning protection is if you are standing on a meadows and you have something that is higher, within 20 meters range, the likelihood is about 95% that it hits the higher point. But this is only likelihood, 95%. So if you are happy with that and you would call this, yeah, that's a success, then I would say yes. But for people, you see, one of the problems with lightning protection is lightning protection, because it's a statistical process, it doesn't work for a single case. So it might be that you still get struck even though you have a higher thing somewhere else. But essentially, the majority of lightning, yes, that would hit into that lightning conductor.
Well, my follow-up question from that was, if that's possible, could we use the power? And you've explained about that. So
yeah, well, that's something that I don't think that's possible because of the timescales, because it's too short. I mean, of course, we can get the power, but it will not. The equations that we find in books, they are made for a static case, but not for a dynamic case. So that's a tricky bit. So we tend to think in terms of statics or apply our equations in terms of statics, but effectively lightning is a highly transient effect because the channel cannot sustain itself. It's a plasma which collapses. If you could sustain the plasma discharge, then that would be a different story. But I don't think that will be possible in the near future.
Right. One other thing is it's an anecdote, really. I knew someone who, through marriage, was related to the family, and is Ukrainian, or he was, he's died now. But he was telling me that in Ukraine, if anybody was struck by lightning, they used to bury them, well, maybe up to the neck in earth for I don't know how long. And I'm just wondering if there is. It seems a bit mad because it's after the event, but there could be some goodness in that.
I'm not exactly sure. Never heard about that.
Your body's absorbed a charge.
Tony, is that if they die, they get buried up to their necks, or if they survive, they get buried up to their necks?
Say this again.
If they die, they get buried up to their necks, Or is it if they survive, they get periductive MX?
Anyone that survives, yeah.
Right, okay.
But it's really earthing them.
Well, there are definitely people who are surviving. I remember that there's one gentleman in the United States who was struck by lightning 3 times. And so he tends to show up in television shows quite a bit. So that was confirmed by medical doctors, because lightning strikes on people, they can be, how to say, determined from the particular pattern that they leave. It's very different from an electric shock that you would get from, so obviously they can distinguish that. So it's like feathering out. It has these, how to say, dendritic structures where the damage happens in the tissue.
Okay, thank you, Tony. Your explanation about the probability of being struck near a lightning conductor explains why NASA has started putting 4 lightning conductors around their launch pads. If you have a look these days, there are 4 masts around, and that's just lightning protection. Okay, so in the room, Tony Morris.
Oh, sorry. Oh, sorry. Hi, Martin. Can you hear me?
Yes, I can.
You spoke about some of these activities up to 80 kilometres. Well, that's the edge of the mesosphere.
Yes, correct.
And that is where we see noctilucent clouds.
Yes.
So is there any interaction between the Sprites and the noctilucent clouds, or are the noctilucent clouds too far north?
That's exactly the case. Once the Sprites were discovered, there were immediately people who put up cameras in the north to see noctilucent clouds, and also polar lights to see what the relation is, or whether there is any relation. But it turns out that there are not many thunderstorms in northern Finland and Norway. Number one, there are not many storms. And second, when there are storms, there are normally clouds around. So as a result, you can't see them. So it's an unfortunate combination. But the idea is certainly going into the right direction. One of the things that I always like to say, the Sprite community does not know enough pilots. You know, it's very easy to circumnavigate clouds. You just need to have a pilot and a plane. But the funny thing is, I mean, I've been talking to pilots over and over again. The problem is that to maintain a license to fly at night is very hard. So it's almost impossible if you don't have a commercial interest in this. The vast majority of hobby pilots, they can only fly during the day. And even that, you need to have so many hours a year to sustain your license. But flying at night is a different animal. So you have to have extra education, and you need to maintain your flight hours. And that's why it's very difficult to find people who help you with these type of scientific questions.
Okay, Tony. Peter Lloyd.
Thank you. Yes, thank you, Martin. Very, very interesting talk. You showed us pictures of red sprites, and you said that this was due to ionization of the nitrogen in the atmosphere. And that made me wonder whether you also get green sprites from the ionization of the oxygen, the way you do with the aurora.
Excellent question. Yeah, people have been looking for that, but no, nobody found it so far. But I know people who are still searching today. They don't want to give up.
All right, well, good luck. Thank you.
Thank you, Peter. We're going to take 3 more questions then. Tom,
can you hear me? Yeah. I just wanted to ask, as a matter of interest, what with regard to lightning strikes, what are we talking about in terms of voltage and current?
Well, the current is on the order of 20, on average, is about 20,000 amperes.
Right.
And the voltages, they are on the order of hundreds of thousands of volts. This is where these large numbers for the power are coming from, because they're electrostatic measurements. So if you multiply the two, then you know current and power, current and voltage, then you get power. And this is where these large numbers of megajoules are coming from.
All right, thank you.
Okay. Ian Hargraves.
Yes. Well, thank you very much, Martin. I didn't know much about lightning before I watched this, so thank you very much for that. I'd just like to recount a little anecdote, is that we used to have, years ago, we used to have a 60, 70 foot high cedar tree at the top of our garden. And one night that got struck by lightning and it blew the whole tree out of the ground, root ball and all. And I thought, you know, when I asked the tree surgeon that came to clear the mess up, he said, oh yes, it's actually caused by the moisture in the ground superheating and forming a steam ball below the tree and blasting. It must have been, I don't know how many tons this tree was, but it was big, you know, and it was just incredible.
Yeah.
And I know you say that the you know, there's gigajoules of energy in there in those lightning strikes, and yeah, you know, that explains why it happened, you know, and how it happened.
Yes, I think you are hitting on a very good point. It's a very nice example. You know, the plasma channel heats up to about 20,000 Kelvin, so it's
Right.
really hot, and that happens very fast. This is why we have the supersonic expansion of the air that produces a shock wave, and that is what we hear as thunder. But because it's so hot, it also has the thermodynamic effect of heating, overheating moisture, which essentially becomes gas, and that wants to expand. And so very often from these movies that you see about lightning hitting trees, you see very often the bark coming off, you know, because the moisture sits there and then it's like an explosive, you know, it just goes away. And unrooting of trees also does happen. What we also have is very often that at branches, they kind of like start kicking them off, because this is obviously where some water is sitting. So yeah, but not all trees that are struck by lightning die. So in Cardiff, there's a lightning lab. They had a research project on tree death from lightning, and they found that surprisingly, even they can survive. So it's a little bit like humans as well. If you are lucky, you can continue.
Well, when I was in America, I was on a plane trip to Nantucket Island, and a guy there had been struck by lightning when he was playing golf, and survived. And he was then going round, you know, advising people who play golfers in various different golfing clubs and that, advising them about, you know, the hazards of lightning. So yeah.
Very good of him. Sadly, in America, a lot of people who are golfing, they got struck by lightning. And I think it's a mix between, how to say, the lightning and the character of these people, because they don't care when the storm rises.
I was going to say, you do not need much instruction to be told not to go away a metal stick around in a lightning storm.
That's right. That's it.
I have some thoughts. So, last question then. Over to Andy Devey, please.
Hi, Martin. Thanks for an excellent talk. I believe that lightning has been detected on other planets through orbiting satellites. I wondered if anybody had actually done any investigation on the imaging to see if sprites had been detected on other planets, or if there's a plan for future missions to put a sufficiently sensitive camera to detect them.
Yeah, I think there is such kind of experiments. In Japan, they wanted to investigate whether there's lightning on Venus, which is contentious. It's known that there's lightning on Jupiter, and for Venus is contentious. And so they had a mission which measures lightning, and they were making some predictions about how a sprite would look like. But I can't recall that I've seen any results from it. And I heard similar speculations about cameras pointing on other planets. But it's very difficult to say whether a blob of light is actually then really a sprite, because you want to have several of these observations. You know, when the first blob of light was published in a scientific journal, at the time I was a PhD student, I looked this up and I couldn't believe it that this gets published, because there was a blob of light on a newly developed camera, which can have all sorts of electronic effects, and it just looked entirely unspecific. Nobody took notice. It started to be believed once NASA had this payload camera, and they were circling around the globe for 2 weeks, and they had like 30 events. And they showed in a paper that this is actually consistent and happens all the time. And then suddenly the scientific community was jumping up and down and started investigating this. And I think it's very hard to reproduce on missions to other planets. I think there's indications where such kind of things could go. And I wouldn't be surprised if there's more planetary missions in the planning. But I'm personally not involved in planetary exploration. So I'm not up to date on that.
Okay, Andy.
Thank you.
Martin, thank you for a wonderful evening, a brilliant talk. I'm now going to go away and contemplating burying people up to their necks after electric shocks and things. But that just leaves us to thank you. So can we have a big Mexican Swinton Astronomical Society thank you to Martin Fullekrug. Thank you, Martin.
Yeah, thank you very much. And thank you very much for having me, and also excellent questions. I enjoyed myself very much. So it was a great experience.